Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on February 1st, 2026, about 4 days ago. It discovers a hidden reward subsystem inside large language models that mimics biological brains, finding that removing just the top 1% of these value neurons causes reasoning accuracy to crash from 75% down to 20%. The paper is titled, Sparse Reward Subsystem in Large Language Models. And as we'll see later, the implications for detecting hallucinations and understanding model confidence are really promising. So to back up that claim about sparsity, Figure 1 presents empirical evidence from the QN 2.5 14b model. The charts plot the AUC, representing prediction accuracy, against the pruning ratio for layers 2, 3, and 4. In the top row for GSM-8K and the bottom row for Math 500, the trend lines remain remarkably stable. Even as the pruning ratio on the horizontal axis pushes toward 99%, the performance doesn't collapse, which confirms that the critical value information is concentrated in a tiny fraction of neurons. Okay, while the previous figure showed that these neurons are rare, Table 1 proves they are absolutely critical. Here, the researchers zero out just the top 1% of neurons in specific layers and measure the resulting accuracy drop on the Math 500 dataset. The results in the middle column are drastic. For example, intervening in layer 5 causes accuracy to crash by 74 points, leaving the model with a score of just 1.2%. In stark contrast, the rightmost column shows that removing a random 1% has almost no effect. Alright, while Table 1 proved those neurons are vital, Figure 4 now maps out their distribution across the entire network depth. Using the smaller QN 2.5 1.5b model on GSM-8K, these 6 panels track the AUC for layers ranging from 5 up to 28. Notice the trend on the right side of each plot. As the prune ratio nears 1.0, meaning we remove almost everything, the accuracy doesn't just survive, it often spikes upward. This confirms that the clean reward signal is isolated in that tiny, sparse subset of neurons, regardless of whether we look at early or late layers. So, having verified the layer-wise distribution, Figure 2 tests whether this phenomenon holds across different reasoning tasks. The grid tracks the 14b model's performance on 3 distinct benchmarks, Minerva Math in the top row, ARC in the middle, and the STEM subset of MMLU at the bottom. Just like before, the AUC trajectories are remarkably flat. Even when pruning nearly all neurons, the model retains its predictive power, proving that this sparse reward subsystem is robust and universal, regardless of the dataset. Well, having shown the system works across datasets, Figure 7 now tests if these neurons stay put across different models. The researchers compared 2 separate models fine-tuned from the same QN base, plotting the intersection over union on the vertical axis against the pruning ratio. Notice how the solid lines for layers 2, 3, and 4 stay consistently higher than the red dashed line, which represents the random baseline. This strong overlap proves that value neurons are intrinsic to the base model and remain stable in their positions, even after the model undergoes different fine-tuning procedures. So, moving from expectations to reactions, Figure 8 visualizes dopamine neurons, which track reward prediction errors. On the left, Panel A shows a positive surprise. Notice the sharp green peak in the activation graph. This spike happens exactly when the model hits a key observation in the text below, realizing it can solve the problem. Conversely, Panel B on the right captures a negative surprise. Here, the red trough marks a sudden drop in activation. This dip coincides with a logical flaw in the reasoning, signaling that the model's confidence has crashed because it detected the mistake. Alright, establishing that functional link. Figure 9 confirms that dopamine neurons depend heavily on the value subsystem. These plots track a single dopamine neuron's activation over the course of a generation. The yellow line shows the original healthy trajectory, while the blue line represents the model after removing 20% of random neurons. You can see they overlap almost perfectly, meaning random damage is negligible. However, the red line tells a different story. When the researchers ablate just the top value neurons, that red signal becomes chaotic and misses the key peaks, proving that dopamine signals are downstream consequences of the value calculations. Wrapping up, this study offers a fascinating glimpse into the internal mechanics of reasoning. 2 takeaways stand out. First, large language models rely on a remarkably sparse set of value neurons to guide their logic, and second, monitoring these neurons offers a powerful new way to detect hallucinations before they happen. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.